and then raise hands. Okay, this is a hands-on session. So being able to actually do this as we go along is important. So I still see only about 10 people have raised their hands out of about 50 who are in the meeting.
Yeah, so let me first give introduction of our resource person
Okay.
today. So good afternoon, everyone. Good afternoon, Dr. Varun and his team. In fact, the team always plays more important role, I know, because my team does the same thing, Jigar and Pratik here. Okay, so Dr. Varun Bali is he has done his PhD in astrophysics from Caltech. Later, he worked in IUCA on postdoc, and currently he is working with IIT Bombay in astrophysics division. He mainly works in optical astronomy. Uh, but I would like to say something more about him. So I also get to speak about myself. Varun was one of the uh, in fact, he was the first Indian student to win gold medal multiple times at International Astronomy Olympiad, and that is where we met. I was supposed to be uh, training some students in physics, and by that time, Varun had already got gold medal, and he started coming and working as a facilitator. So, in fact, he was more of like my colleague, and we together discussed things. And he, being very young, creative, intelligent, really gave many of us, the ideas of how to design new problems, how to think of, and we even today we enjoy one. Sometimes if I have some kind of difficulties, I do call Varun, and he responds to the ideas. If I once in a while make something really good, I feel I surely like to share with him, because his appreciation is something that I really care for, and because he has his own creative mind. And now today his team, I mean, see, that is an advantage of becoming a teacher. I mean, it is one of the best profession where you might have uh, told something sometimes, maybe just once throughout the life, you can say, he was my student. Always we can do that. That is the best part of this profession. And before everybody joined, his team had joined here. So I think Gaurav was there, Kriti was there, Akshat is there, and Gaurav told me that 5-6 years back I had given one lecture in Kritika, so he remembered me from that time. So that's the best part of it, and all these intelligent young people here in the party as a participant. I'm just advertising that how good my field is, that how we can take credit of others' work. Okay, I mean, not
No,
officially.
I
So
think there is one more way to look at it. You are also responsible for everything that happens. So if today's
yeah,
lecture is boring, then Mahesh sir was one of my first astronomy teachers. And also Gaurav says that you are responsible for him getting so interested in astronomy. So one of my PhD students is also you are responsible for. So
okay. So
and apart from the three you mentioned here, Simran Joharle has also helped with preparing today's content, but she had her own college lecture to attend, so she cannot join today.
okay. Okay, so we have Dr. Varun and his team talking about over last 2 weeks. You have explored Python and computational physics also through Excel. What Varun, I told Varun that he is most probably going to disappoint me by showing the power of Python, that I will feel bad that I was good at Excel. But Varun, yes, it's your forum now.
So slide number 4 or 5 is explicitly designed with the intent of showing off how good Python is as opposed to Excel. But with that, hi everyone, good afternoon. So let's get started. I am Varun Bhalirao and I'm part of a group we call ourselves Star Lab at IIT Bombay, which stands for Space Technology and Astrophysics Research. And today here I'm going to talk about doing astronomical calculations with Python. Okay, and my job is straightforward. I'm going to be here, talk for 5-10 minutes, say hi to everyone, then I'll run off, basically go into the background, let the students and postdocs do all the hard work, and then I'll come back to take the credit and get all the claps. So let's get started. Okay, so since we are talking about astronomical calculations with Python, let's start with a calculation. Okay, and let's understand how we step up through that. So I'm going to give you a very simple, straightforward problem to solve. Okay, let's calculate the revolution speed of Earth around the Sun. Let's assume circular orbit. Okay, so you all, I'm sure, know the formula. You can start by equating centrifugal force to gravity, and it gives you V is square root of Gm by R. So you have this formula. Now you want to get the answer. How do you go about that? Okay, so the first thing is that well, let's note down what G, M, and R are. Depending on what kind of an astronomer or a physicist you are, you might use G equal to 1. If not, you will at least say M is 1 solar mass, R is 1 AU, and then you will get V in some weird units which have kg, meters, AU, solar masses, and so on mixed in. So let's first try to remember the SI values. That's usually problem number one. So you have G over here as 6.67 into 10 raised to minus 11. You have 1 AU, convert that to meters. Turns out, fortunately, numbers here are easy enough for you to solve directly. Okay, so you have in the numerator 10 raised to 30 and then minus 11 here. So that's 10 raised to 19. Another 10 raised to 11 in the denominator. That leaves you 10 raised to 8. So you can bring out 10 raised to 4 here. Great. And then you have 6.67 into 2 divided by 1.5. So that's about 9. So square root of that is 3. So you get 3 into 10 raised to 4 meters per second. Okay, good. One of those rare problems where you actually can solve it mentally and get a good enough answer. If you want to go be more accurate about it, or if you want to do this faster, well, first thing is you could go to the trusty old log tables. Uh, I don't know how many of you have actually used log tables, but I have, and I also remembered a bunch of logs and anti-logs by heart. They still prove useful at times. But usually you would all directly jump to this step where you can actually use a calculator for this, right? And that is just making your calculations faster and more accurate. Okay, and then why not continue up the ladder? So yes, you can actually write a spreadsheet for this. So you can create your cells. One of your cells can be your R in AU, because if you want to do this for other planets in the solar system, for example, you will actually speak of distances in AU. You write another cell for converting the AU into meters, and then you can keep copying those cells and so on. So you can actually make your calculations much faster. Okay, but then if you want to go into another direction, you can actually start doing coding. But just coding is not important. You have to code with the right tools. Okay, so I'm going to show you very few glimpses of what we can do in Python. You will not necessarily understand everything that is going on right now. That's okay. That's where the hands-on session and the rest of this talk is going to be about, so that you'll understand things better. And at the end of it, when you come back to this, or when you go through the advanced resources that I will link in the end, you will understand this and you will be able to do this by yourself. Okay, so the tool that I'm going to talk about is Astropy. It is a set of libraries in Python for astronomy, just as you have used NumPy or probably SciPy. Matplotlib Astropy is yet another package. Okay, so here is how we'll solve the problem with Astropy. Let's start with importing things. I will, of course, use NumPy. Then from Astropy, I'm importing two things. I'm importing something called astropy.units and something else called astropy.constants. Okay, and then my calculation is a single command. Okay, remember our formula from 2 slides ago. It is square root of G M by R. So I have here constant dot G, constant dot mass of the sun divided by 1 AU, and that is the velocity of the earth, V underscore E. And I can tell it to print it in whatever units I want. So I told it to print the VE in units. units of kilometers per second. Okay, and here's the answer. Right, so in one line I did the calculation, one more line to print, and that's it. In fact, I literally typed only one line when I actually did it, because I have set up my Python environment such that these are all done by default. Okay, now suppose we want to up the game. Okay, let's see what more we want to do. So if you so suppose this is the sun, this is the blue one is the orbit of the earth, red one is the orbit of Mars. Okay, you could do the same thing and calculate the speed of Mars as well, right? Speed of Mars is going to be lower, r is in the denominator in that equation. But now what I want is that suppose you have a phenomena, a setup which we call opposition. So I have sun, earth and Mars in a straight line, as you would see here. So earth is here going this way, Mars is here going this way. I now want to calculate the angular speed of Mars in the sky as seen from earth. Okay, so how would you do that? Well, let's start with the same thing. I had calculated the velocity of earth. Now I replace simply one thing here. In the denominator, instead of 1 AU, I am saying 1.52 AU, which is the average distance of Mars. I am again assuming a circular orbit here, but there are tools which will let you query the exact coordinates of Mars, the exact distance, exact everything. Okay, so this is velocity of Mars. And now to calculate the angular speed, I simply say omega is v1 minus v2 divided by r1 minus r2. Okay, so the separation between Earth and Mars is 1.52 minus 1 AU. The velocities I'm subtracting. Radians is a unit I'm explicitly adding here. Okay, so I have some value stored in a variable omega. And now again, using the right tool, all of this you could have done in C, you could have done in any other language that you imagine, right? But the advantage we are getting is that it knows what G is, it knows what M sun is, it knows what AU is. Okay, it has a bunch of units pre-programmed into it. So here is how I can use this now. I can tell it to print omega in arc seconds per minute, so that Mars is actually doing what is called retrograde motion. So when it is at opposition, Mars seems to go in the wrong direction in the sky, and it is moving at 0.89 arc seconds per minute. Instead of that, I want to say, okay, I observed Mars tonight. By tomorrow, how much will it have moved? I can tell it to print in units of degrees per day. And here I have it. The answer is minus 0.36 degrees per day. Right, so a whole set of calculations. Now these are very superficial calculations that I'm showing you just to show you how quickly we can get some important aspects done. But let me show you what else we really do in Python. Now here in general, why are we going towards coding? So there are a few important factors behind this. Okay, and in general, you want to make your life easier. You don't want to be using log tables. You want it to be faster for you. And this is something I'll talk about in a minute again. Third is you want it to be more accurate. Accurate is not just the number of digits that your computer prints out, but accurate also means the human in the loop. You want to make sure that while doing your calculations, so one of the things that I used to keep doing in school is that if I'm solving a sum on one page, at the end of the page, when I have to turn the page and copy over the number to the next page, I would usually make a mistake there, right? So that's losing accuracy. From here on, I'll do a correct calculation. Up to here, I'll do a correct calculation, but my final answer will be wrong, because instead of copying 12.3, I would copy 13.3. Okay. So, and then finally, everything has to be reproducible. Whatever your code does once, it has no random aspects involved in it, unless you specifically put in Monte Carlo or other random numbers in it. But your whatever processing you did, you have to be able to get the same answer. And that is something that is extremely important in science, of course, where you want to make sure that your work is completely reproducible. Now, when I talk about faster, there is an important part that I want to tell you, especially because we are doing Python here. Okay, every now and then some student comes to me and says, but sir, C is faster than Python. I'm willing to challenge you that my Python codes will be faster than your C codes. Okay, C can be faster than Python. This is like saying कि यार builder ने घर खराब बनाया है, you know, इससे तो बेहतर मैं बना सकता हूँ. In principle, yes, but for that you have to learn how to do construction. You have to get all the material. You have to take all those precautions and then build a house. You don't build one yourself, right? You builder को गाली देना पड़ा तो भी you buy it from a builder. because they still know better than you do, right? So knowing your tool very well is very important. And also the development cycle has to count as part of the speed. Okay, for example, this last answer where we calculated the omega for Mars, okay, it took me about 2 to 3 minutes to write up all of those examples and make my slides. Okay, if I have to do this calculation for say Jupiter right now, the bottleneck for me is going to be looking up the distance to Jupiter. If I had to do all of this in C, it would have taken me about 10 minutes to make sure the code is compiling properly. Then next time I want to calculate the angular speed of Jupiter instead of Mars, I have to change all of that. So your development cycles are long. Your code runtime, instead of being zero point 0.1 seconds, it would have become 0.09 seconds. Who cares? Okay, so keep all of that in mind. You have to have your eyes on the final goal. You have to make sure that easier for you, faster for the entire development and getting results, and then reproducible and accurate results. Okay, so I'll show you some examples of how we actually do coding in Python. Okay, so we operate this telescope in Ladakh called the Growth India Telescope. We were the people who set it up. And if you look at the entire workflow, okay, it starts from very complicated. I of course don't expect you to read through all of this right now, but it starts from, suppose there is a gamma ray burst somewhere. We have codes that actually listen to that pay attention to sources online, identify the burst, send commands to the computers at Hanley, take the data, actually point the telescope there, take data, get it back, process it, find the transients and show it to us. All of these codes are done in Python, all of them. Okay, so here's an example. This was just over 2 years ago, a gravitational wave event, and the North Polar region. This is the region that we actually observed with the Growth India telescope. Needless to say, all of the plots that you are seeing here are plots made in Python. Um, the coverage that we did, okay, here are the places where the telescope pointed, each square tile. Where to point the telescope on every night was calculated in Python. The actual pointing was done with Python. The actual observations, downloading, everything was done with Python. Okay. Then once we had the data, all of the data was processed in Python. After that, we took reference images, we subtracted them, we found these transient sources which had become brighter during our 10 days of observation as compared to older observations. Here are their measured magnitudes. All of this was done in Python. And then finally comparing those, so we did not actually detect a source. Those five that we detected were too flat, so we said these are not kilonova counterparts that you expect from gravitational wave events. All of these upper limits, these theoretical models were all loaded up and calculated in Python. All the comparisons, ruling out these most crazy ejecta scenarios, and all of this is all again done in Python. Okay, so with this introduction, let's do this. I'm going to hand over to Akshat Singhal, who's a postdoc here at IIT Bombay. And Akshat is now going to actually walk you through the
To
notebooks.
achieve this, we're going to be adding in a UV sphere, adding a material, and giving it a fire
Thank you,
simulation.
Professor Varun.
Now, this
And
is
that
going
was a
to be
nice
a little
talk.
bit of a
Akshat, there is
stylized,
some
so it's not
audio
going to
we
be
are
basically
hearing from
accurate,
your
more of the
side.
scale of it. If we wanted it to be the exact size of our sun, we would have to scale it up by
Just a second. Is it?
Just mute.
347,755,000.
I'm hearing a lecture about the sun from your side just now.
Okay. Right.
Yes, that has stopped it now. Okay, go ahead.
I'm sharing a screen. I hope you guys are able to see it. And most of you have the access to that Google Colab link we have sent you, and you have a new notebook with you. I still see a lot of hands down right now.
I think Google is lowering the hands after a short interval.
Okay, okay.
So everyone, please lower your hands. And if there is anyone who is having an issue in accessing the notebook, then you should actually type in the message box that you cannot access Google Colab or you cannot access this particular notebook. Okay, so no issues so far. Akshat, you can get started.
All right. So, hello everyone. I'm Dr. Akshat Singhal. I'm uh, will be uh, giving you a tour of this libraries and Python and what all things we can do with all these libraries. I believe that you guys have done some coordinate conversion on Excel already. We will have a walkthrough using Python as well. So all those who have access to the
I'm sorry to interrupt. Can
yes,
you enlarge your screen? It's difficult to read.
okay, it's not enlarged right now.
Can you
No,
zoom
We
in?
are
the
seeing your full window, Akshat, but the font size is too
Okay,
small.
I
If
see.
you can
Okay,
zoom in, fine.
Just zoom in locally there. That's all. A couple of more zooms is good. Yeah. Uh,
right,
Meanwhile, why are we using this instead of Jupyter? These are Jupyter notebooks, Aruna. The only reason we are doing it here in Google Colab is that the prerequisites that you have, Astropy and so on, are pre-installed on Google Colab. We did not want to spend time in trying to set up everybody's machine, but you can do all of this offline locally also later. So if you just later take note of all the modules that had been imported here, then you will be able to install them with pip as usual, and you'll be able to execute all of this in Jupyter notebooks on your own machine as well.
right. And the one we have shared you two links. From one you have to create a new notebook, and from one you will be given access to a copy of this notebook which we are working on. It's a view only, so you cannot run anything. We advise you to copy paste from there and run yourself in your new notebook. All right. So as usual, we start with the basic importing. Import NumPy SNP is the standard. We will require time as well. This library. So we can begin. So I expect you guys have run this already. Is this a decent enough speed? Can anyone can unmute and say yes?
Yes.
All right. Great. So let's talk about coordinate conversion. So astronomers like to measure the position of certain objects in sky in different coordinates. One is called equatorial coordinates, where we tell how at what angle the object is with respect to the plane of equator. So if you assume a plane that is passing through the equator, and what angle in the sky a source is making, that is your declination. And similar to what we have longitudes on Earth, if you somehow project, if you expand that and project on the sky, you can also have longitudes, and based on a reference, we assign uh, how much how many degree clockwise we have to move in order to locate that sky, that object. So these are some coordinates. So instead of having your base plane in equatorial, you can have your base plane in some other plane. uh, we also like to have that plane passing through Earth and Sun orbit, that we call ecliptic plane. And if you measure things similarly, you will your coordinates which were having certain values in one frame will now be changed. So it's a useful exercise to convert one coordinate system to another. This is a nice fancy formula you will see. 10 delta equals so and so. In the copy that you have, I have modified delta to delta E. That stands for the ecliptic one, and delta over here is for the declination. Apologies for this confusion, but everything on the left hand side is on the ecliptic coordinates. Everything on the right hand side is in the um, equatorial coordinates. For this, we require one more constant, that is the obliquity of the ecliptic. That is at what angle the plane of equatorial and ecliptic they differ. This is a crude diagram that shows the plane of equator and the plane of ecliptic. So any if there is a source on the sky, at what angle with respect to this equator it will have, and uh, as you have learned in your spherical uh, coordinate system, there is also a phi angle, azimuthal angle. So something similar along the plane, be it ecliptic and equatorial. What phi angle we are referring to? All of these have a reference. There is a, you can assume a vector in the sky pointing to Aries, one of the reference stars, and from that star, what is the uh, coordinate system? You will require a plane and a coordinate axis. Based on that, all of the angles can be predefined. I hope we are clear at this point. Any questions?
Just that question, tan delta that you written at the top, should that be lambda or?
Actually, yeah, that should be lambda. Let me
Okay.
quickly. Yeah, I think now it's. Oops. Yeah, I think this is more appropriate, and we can now learn the conversion. So if you know your equatorial, you can quickly get your ecliptic coordinates. Right. So let's start with writing one function. So in an argument, we pass RA and det. That's their common astronomy names. So instead of right ascension, we call them. I mean, right. Basically, this is the alpha, and this is del. Right. So let's recreate this formula into our function. So we have to first pass the epsilon value. This is a constant we will require. So we assign a variable ESL. It's in degree. Most of your Python packages, whatever argument you provide in trigonometric function, they automatically assume that user has provided them in degree, in radians. I'm sorry, in radians. So if you and astronomers would love to work in degree because these are nice numbers ranging from 0 to 360. People like to work on that. It's more intuitive for them. So if the user has provided them in degree, which people usually do, you convert them into radian. So RA, deg, and epsilon, in degree, you have converted them into radians, and then you calculate sine of RA times sine of times cos of epsilon, which is the formula sine of alpha cos epsilon plus tan delta sine epsilon and so on. So you can calculate this, store it to a variable term 1. Similarly, you can calculate the second term, tan times declination times sine of epsilon, stay with that term 2, write term 1 plus term 2 divided by the denominator cos of RA. Now, why haven't we done this entire thing in just one line? You could have just wrote plus over here and then uh, divide by the denominator. It's usually nice and neat to write them in separate lines so that user knows. Otherwise, you will have too many parentheses, too many terms going on. It's often confusing if you go back to this code a month later or sometime later. So it's a nice practice to break it down. And since this formula will give you tan of the angle you want, you just want this angle, so you have to take tan inverse of the right hand side, and that's what we do next step. np.arctan, that's arctan is also a way people call tan inverse. Tan inverse is a larger term, so arctan is more popular to be written in Python. uh, you will also find another package called arctan2 that is useful when you have infinities and other stuff involved. So far we are fine, and this will also return you the value in radian. So since, as I said, astronomers like things in degrees, so we convert this into np.degree long rad, and we get the longitude. Similar calculation we do with the latitude. Here we have to take sine inverse. We calculate the same way. You can copy paste this code, and you will get the latitude. And then you can print, you can return, and you get your values nice and sweet. So has everyone copied this cell run themselves understood so far? I mean, any questions or any issues? All right.
No, sir.
So I will take it as okay. Good. Thanks. It's like if it's good to have some feedback. So don't be shy to unmute yourself and say yes, no, or something. Right. So let's now calculate the change in equatorial coordinates of Betelgeuse. That is a star in Orion constellation, and these are the coordinates in degree you will find. You can easily search them online if you want to know about any particular star. You will find such coordinates easily. Now let's calculate what these coordinates will look like in ecliptic, right? So we start with defining RA and DEC as this, and we say, okay, let's run this.
Akshat, Akshat, let
Yes.
people run it and let them calculate the answer.
Uh-huh.
So people, please go forward and run this. And when you have run it, when you have an answer, raise your hand. Okay, if you have any doubts about what has been done so far, then stop, ask questions, and proceed. So copy this function, paste it in Google Colab, or if you have these libraries installed locally, you can put it there and then try to do this. Once you have done it, please raise your hand. Yeah, so I see 3 hands up so far. We'll wait until that number goes up substantially. Um, being a person used to online teaching, I have a lot of patience here. I can just sit here and wait for like half an hour if I don't see enough hands going up for half an hour. So we can play this game for a long time. Okay, so please go and actually raise your hand if you are done. So I see about 10 people are done so far. That's 14, 16. Good, now we are picking up speed, 20. Okay, so Apeksha, you can please unmute and ask what issue you are facing. Apeksha, what warning were you getting?
Hello, can you hear my voice?
Yes.
Hello, sir. It shows that this notebook was not authored by Google.
Oh,
It
yeah.
shows this warning.
And
Yeah.
just run it anyway. Oh no, you are probably trying to run this on the
Don't run the notebook that Akshat has shared.
ah,
You copy paste it into a
right.
new notebook yourself. Okay.
You can copy paste these
Okay.
commands in your new notebook and then run it. I will give you another 5 minutes. That will also keep you on board how this flow work will go. So it probably should take you extra 5-10 minutes initial stage, but I expect as we go along you get used to it and we can quickly copy paste and run these lines. Okay. If you take too much time here, I have to cut short some of the time in explaining certain things and exercise problems. So
There
try.
is one more option on Google Colab, that copy to drive, so they can just save a copy and run that in their own drive.
We did consider that. Copy paste karne se you think at least a little bit more about it. So that's the
Yeah.
advantage.
Okay.
Because then you can run the entire Jupyter notebook and then set ideal for the rest of the lecture. So that will be less useful. At least if part by part you are understanding, looking at the code, that is helpful. Yes, it will be slightly more work, but you will probably learn more. Professor Varun, are there enough?
Yeah, I think we can continue.
Right. Also Gaurav, I would love if you also take care of how many hand raise or if there is something.
Yeah, I'm just having a look at the chat. So, if you are stuck somewhere and if you want to ask it in the chat, feel free to do so. There are others who are having a look at the chat.
So Gaurav and Kirti, Gaurav and Kriti in this group will be helping you with this thing. And also, since I'm screen sharing, I won't be knowing your chats immediately. All right, thanks. So, okay, so you must have gotten this answer. We print what RATech was, and then we print these are the new coordinates. So, from 88, the longitude was roughly the same, only a few decimals changed, but your declination changed significantly from 7 to minus 15. If you want to do it by hand, by calculator, that is still fine. But what Python allows you to do it for a bunch of these coordinates. If there are hundreds or thousands of these coordinates and you have to change it quickly, we will learn how to do that. So for that, we will require use of library called Astropy. You have just seen a small flavor already. So now let's see how that library can be useful in writing these codes. So these are just a doc string explaining what the arguments are. Again, there are R and tech in degree, and we return ecliptic coordinates. We print certain commands, just the user know what all things are done. It's correctly. So Sky code is one of the library module Astropy provides. We have to tell that these are coordinates in Sky. So we tell array equals this number. You multiply it with unit u dot degree. So I mean every number has a magnitude and a unit. So you don't say how much you weigh when someone say 10, you say 10 kg, you say 10 pound, you say 10 gram. I don't know a person who weighs 10 gram, but you got the idea. So that value 10 and that unit gram is also important, or kg or whatever. So similarly, it is useless for us to tell just the number, because you also have to tell the unit and it's multiplied to the number. We do the same for degree, sorry, for declination in degree, and we tell a frame ICRS. I will not go much into the detail. It's a standard frame we use. We will come back to it at later point. But this is a syntax requirement for this Sky code. So we define this in one variable, and then we simply say whatever this coordinate is, you convert into geocentric ecliptic. So, and that's it. And whatever this value is, it gets stored. It gets stored as a structure, not exactly as number you would like to print, but these have methods, and from this variable you can extract those numbers. Just write that variable dot lon, and you will get longitude, ecliptic longitude. That variable dot let, and you get ecliptic latitude. Right. So this entire part, if you see, from here, converting from radians, then calculating term by term, then calculating for declination, all these things got reduced to just these two lines, right? So it gives immense advantage to the user to be able to quickly write, quickly. It gives less opportunity for errors, and that makes Astropy a lot more advantages. Right now, let's run this again for the RA. Since RA and DEC we have already defined for Betelgeuse. Here, RA and DEC, even if you define, those are local variables, so they won't change. So let's run all of you for using the same but Astropy module and see how the results differ. I will again wait for you to raise your hands. Uh, Gaurav and Kriti, you can let me know if there are enough hands raised.
Yeah. So once Akshat starts on a different cell, make sure you lower your hand so that we know that people have done the next one as well. if you are stuck somewhere, feel free to unmute and ask. Right now,
Yeah, as I understand, there was one question. I didn't see the chat. There's a question that your answer is minus 88 something rather than plus 88, whatever it should be. I think these kind of issues come when, since the code is same, I don't know why it will happen. But depending on how many decimals you have copied or uh, certain other things. Sometimes sine inverse, cos inverse gives different answers because they are. In fact, that was one of my talking point in this talk as well. That sine inverse and cos inverse, they give you values within uh, minus pi by 2 to pi by 2 or minus 90 to 90 or 0 to 180. But these coordinates will span from 0 to 360, for example, RA. So it's much more difficult to make sure that you write your code for all these cases properly. Sometimes because cos theta is cos 80 degree is same as cos minus 80 degree. So your Python program can sometimes get confused if you don't provide it accurate enough information. All right.
there's one more. Just 1 second,
Yes.
Akshat. There's one more question in the chat that someone got this error that skycode is not defined. So you probably forgot to like copy paste this one cell from Astropy import units and from Astropy coordinates import skycode. So once you copy paste that, run that, you should not get this.
Yeah. This is one cell that is there. So at least copy paste some of the cell continuously so that you are on board with us. So it's nice you are getting these
One
errors.
question.
Yes, please.
See, in the earlier code, the answer was some minus 15 something, and here it is minus 16. So is it because that epsilon is defined slightly
Right.
differently?
Yes, yes. So these are more exact, and those were some crude values, anyways. It's not recommended to work with sine inverse, cos inverse, just directly. Just you saw.
So let me chip in here. Okay, this is exactly actually exposing the importance of libraries. Okay, for example, what is the inclination of Earth? Okay, you'll all probably say 23.5 degrees, but is it 0.500 or is it 0.499 or is it something else? And it gets a lot more complicated than that. When you're working with coordinate systems, there is precession, which means coordinates change over time. What frames are you using? For example, you saw a word there called geocentric to true ecliptic. If you are looking at coordinates of the moon, for example, whether you're observer centric or geocentric matters. So all of these things, when you're writing a library, okay, or rather when you're using a library, the people who wrote the code have fixed problems that you don't even know would have occurred. So when you use this function where you're using Astropy to convert coordinates, you're never going to have these nasty surprises of rounding off errors, of array coming negative instead of positive, or things like that. Okay. So that is the key factor over here why we try to use libraries as much as possible and work in an ecosystem where people are actively working with the same set of codes.
Now,
Right.
Dr. Akshat was mentioning tan 2 also.
Yes.
So is it similar to the tan 2 that we use in Excel, where
Yes.
x and
Yes.
y
Yes.
coordinate
Yes.
you give and you
Yes.
get
Yes. Yes.
answer in? Yeah.
So these are now common modules in across all libraries. From MATLAB to R, everyone use this because people have realized infinity and negative denominator numerator stuff cause a lot of issue. And if anyone tries to write their own code, oh, I will make my own. I will have an if else conditions. I don't know how many of you are aware of if else branches. But if you say, okay, if I have negative numerator, negative denominator, or infinity somewhere, then I will take care as a special case. That will make your code immensely slow. I know some of my colleagues who try to do this in an integral function, and in an integration you have to calculate that multiple times for every step, and that made that code like 1,000 times slower. So that's why you can trust these programmers who have made these libraries, because they work at very high efficiency, which randomly written code in C or Python out of curiosity won't have if you're not trained enough, right? And yes,
Akshat, I think many people have raised their hands by
okay,
now, so
great,
maybe we
excellent.
can.
So now we will go the other way. This is an exercise question for you. You have this formula for you. You know the latitude and longitude. Let's say, okay. So beta. Just let me check what we have. Yeah, beta is your latitude, and delta is your longitude. So create a function that, given longitude and latitude, you can calculate RA and DEC based on this formula, and write your own code. Uh, right now we will not use Astropy module, just the standard way as we have learned in the previous cell, previous to Astropy. Just write the code by yourself, okay? Because Astropy will be too easy, and so we want you to have some fun with making your own function of this conversion. In your in the Google Colab notebook, there is no answer for that, so don't try to sneak in. This is something you have to do it yourself. And then you will tell me the answer, at least one of you. What is the RA and DEC if ecliptic coordinates are given as follows? And raise your hands once you are done.
I believe the hands that are raised right now are from the previous exercise as well itself.
So
So can you please
lower
lower
your
your
hands
hands?
down and then
Thanks.
re-raise afterwards.
Great. Perfect.
Akshat, it will be useful to actually have checkpoints in between, just catch up on where people are so far and where they're
So,
done.
so first step, everybody should be knowing, irrespective of how they are writing the code. Make sure that in the function you add, that these arguments will be converted to radians, because astronomers work with degrees. So convert them in radians so that they are Python packages friendly. If for example, you write np.sine of 90, you expect the answer to 1, but it will not read it as 90 degrees, it will read it as 90 radians. And you will get answer according to that. So that's how uh, NumPy modules work. If you want it to consider a degree, you have to tell it specifically, uh, but it's usually better to convert into radians and work in that way. So this part, I believe most of you should have done. If you forgot this, quickly add this, so you can do, and then it's just matter of using those trigonometric function. So trigonometric function will be np dot sine, cost, and whatever you want. In parentheses, your desired angles, which you have converted in radians. So I would recommend splitting them in different terms and then adding and dividing them later. Or if you are lazy and you want to quickly finish your code, you can convert them into one line, but that causes some problem of parenthesis mismatch. That is less recommended. How many of you have done for at least one of the angle? You have written the part in the function. Raise your hand.
If you're stuck somewhere, there might be others who are also stuck at a similar point. So feel free to unmute and ask or paste it in the chat.
There, for this much time, there are a lot of hands not raised. So yeah, you're right. A good question. Just write np dot arc10. You will see one of this function above, arc10, right? This one. So for sine inverse, you will write arc sine. For cos inverse, you will write arc cos. So whatever inverse you want to find, np dot arc followed by that trigonometric function. That's how it works in NumPy. Okay. If you are looking for sine -1 type of function, that doesn't exist. Just people don't like to work with such a nomenclature. Someday, if you write a new programming language, do introduce. Okay, others can lower their hands down. So I will have ask another hand up when you have at least calculated the inverse trigonometric calculation for the second ang- uh, angle as well. So as soon as you have that done, so both angle at least you have calculated. You have not returned, you have not printed, but at least part calculation for two angles are done. Please raise your hand. Okay, one person so far out of 50. So I think this is slightly easier one, so I will give you some part. It's just you have to calculate your numpy sine times numpy cos of those angles. Read carefully what all angles are required. If you want a refresher, delta is your longitude and beta is your latitude. Okay, so it may be some of you have swapped. It's okay. Just change your code quickly, and from longitude latitude you should be able to have this function ready. Quickly write these terms. Um, we have to speed up, otherwise we won't reach the end of the modules. So right, so let's just walk through. Term one is sine times cos, sine of longitude times cos of epsilon. That's what we have. Yes, sine of longitude plus cos of epsilon minus tan of latitude times sine of epsilon divided by cos of longitude. Right, that's what we are doing. Sine times cos, tan times sine, of course with different arguments. Then term one minus term two divided by cos of longitude. In the previous conversion, it was term 1 plus term 2. Obviously, when you change your coordinate differently, signs will also change. Similarly, you will have your declination calculation: sine times cos, cos times sine for latitude, epsilon, longitude. You add those terms and that's it. You get this because the formula is slightly more trivial, no denominator. Obviously, you calculate the tan inverse and then sine inverse, convert them into degrees, and you have this answer. You can print it nicely. If someone is not able to understand, this is just a function that converts your number into string. You can add multiple strings, and they will just join together and make a bigger string. But numbers are not strings, and Python doesn't like to add a string with a number. So you convert a number into a string, and your Python numbers can have multiple decimal places. Python doesn't know the importance of significant digits, what physicists have. So irrespective of what your numbers are, it will just give you arbitrary large number of decimal digits. So you say, just give me a round of whatever value you have to 5 decimal. So you use round array comma 5. That will limit your decimals to 5. Convert this number into string. This is what this entire thing will do. And we have just added array equal to plus string plus to make it simple. There are other ways to do this as well. And then you will return these things. So when you run your code with these values and run this cell and everything is done correctly, you will these array and dec will be stored in these variables, which you will print anyways, and then you can, if you want later, you can use array and dec separately. How many of you reached here so far? Raise your hand. And if you haven't reached and your hands is raised, lower your hand. So one of you probably have sent an answer. Are you asking if this is correct or not? Or yes, there is a problem. See, in one of the answer in the chat, you have made that classic mistake. You have given it np.cos of ecliptic, sorry, epsilon, and you have just mentioned 23.4. Although we have trained ourselves to write sine 90 degrees and 45 degrees, Python doesn't know this. Python assumes it is 23.4 radian. You wanted to say 23.4 degree, right? But Python is confused. So at some place, it's nice for you to convert this to radian value. And also in the answer in the chat, I see every time there is epsilon, you have uh, mentioned it manually yourself. Now let's say you realized, oh, it was not 23.4, it was 23.5. So every place that you have written, you will convert 23 point, delete it, write 23.5, then again somewhere else, somewhere again somewhere else. some of you will say, okay, I will use find and replace, quickly convert everything. Yeah, let's say it is a simpler number like 2. So there will be a lot of 2's in your code anyways. If you find and replace everything, it will cause an issue. So it's better to define a variable so that whenever you have to change something, you can quickly do it just by uh, changing one line, right? Gaurav, Kritika, Gaurav, Kriti, are there enough hands up?
There are few people who have raised their hands. There aren't enough, but I think most of them must have understood the module by now, and I think it's better to go to the next one
Yeah.
now.
So, right. So let's. Yeah, you can refer
Yeah,
to.
just show. Yeah, good.
All right. So now moving to the Astropy module, how you can. So I'm sure you must be a little bit, annoyed by so much writing, copying. Even if you have formula on the same screen, uh, constantly checking up and down, making sure everything is correct, converting degree to radian must be little tiring. So here is the nice, cute version just with the Astropy. So similarly, we will do with Skycode. We will define this time we will not say RA equal to or det equal to because these are different uh, coordinates. We will write ln equal to your variable times in degree, lat equal to your variable in degree, and frame we have to tell instead of ICRS, geocentric true ecliptic. Um so it will automatically knows what epsilon to take, where what the reference planes are, everything, and it will give you quickly your we will assign you the correct variable. For converting, you just say the variable name dot ICRS. If you remember, previously it was variable name dot geocentric true ecliptic. So that's so just writing a different frame. There are other frames also you can use, galactic frame or other stuff, and then you will this variable will be assigned. To get those values, just write that variable name eq in this case dot array to get right ascension dot dec to get declination. So that entire hassle we did for just now boiled down to this. So and this is not something that you have to memorize or you are expected to learn. In fact, I have not learned most of them myself. Whenever I need it, I quickly find it online. Someone has written in the documentation or in somewhere on a blog. I copy this. I have enough understanding where my longitude goes, where my latitude goes, whether it's for RA depth to longitude or vice versa. And with that understanding, I can quickly do it as part of my code. But the best thing is, it saves me from a lot of hassle, right? And if you run this code for long and lat, which we have already defined, just run this cell, and you will have your all the coordinate conversion done fairly easy and quickly. Okay, everybody here so far, raise your hand.
Yes, sir.
Okay, still less number of you, but anyways, I will wait another minute, and irrespective of hand, so will move on. So if you haven't raised your hand button, yes, Gaurav.
Yeah, so I was just going to ask for the same. So in the Astropy usage, if anyone has any doubt, please ask now, or else yeah, we can then move.
Okay, those who have finished so far, they can run this line exclamation mark pip install astroquery. So astroquery doesn't come by default with Google Colab. So we want this library to be installed, uh, and you have access to, because we will get you a lot of coordinates and then do something similar, okay, and see how much time it takes and all. So those who have finished, those who have raised their hands, just run this command meanwhile. Okay. If you are lagging behind, just make sure you have copied at least part of it, and you can run it later, and skip certain things if they are bothering you. Post it in us, mail us, or type in the chat. If something is fundamentally not understood, we will get back to this and quickly reach to this cell, because there are some time consuming cells which are upcoming. The entire astrophysics is not about just coordinate conversion. That's the easiest part. We will get you to the slightly more difficult part.
Just one
Please.
question here.
Yes.
You have mentioned about units, so naturally we can write RA in our minutes, right?
Right.
Yes. So I'm including things to various links to various things that we are doing as we go along. So I'll also include a link to Astropy coordinates and how you can actually give coordinates in hours, minutes, seconds, and so on. So here is an example where Akshat is already showing that. Another thing for people who might be falling behind right now, it is okay. Try to understand whatever you can, but what we will do is the same notebook that we have shared with you. We will actually also put in all the answers in the end. Okay, so any place where we are telling you to write a function and so on, you will even if you can't solve it yourself right now, you will have access to that answer later. Okay, so in the interest of time, we can probably move on now. Akshat, go ahead, please.
Yes. So I'm assuming this part is done. Just quickly run uh, this part, and even if you can't see copy, just type it quickly and run this, because this is essential. We will use this library a couple of times. So just underscore exclamation mark pip space install space astroquery. Run it, and in just few in just small time, it will make sure that library is installed and you have access to it. And then we will import from astroquery.visor import visor. What it does, it has access to a lot of library of stars and sources. So in this cell, what we are doing, uh, we will give some array and deck. Here we have randomly chosen 56.85 and 24.1, whatever, and we are telling them that within a certain box size, radius of this many minutes, arc, you have degree, minutes, and second, and these many minutes, 20 minutes, give me all the sources that you have. We provide some, you don't have to understand and go through all of these, don't worry. We provided some catalog number, and it knows from where what to give you. And among a lot of stuff, it can extract it for you. We are asking just to provide us object ID, array, and deck. You don't have to understand what this cell does. This is not part of the course. We have to study this in much detail. This is just part requirement for the upcoming cells. So don't worry if you don't understand this. This will require some detailed understanding. You can read about Visor in general, but right now it's not recommended. It's a slightly advanced version. If you are interested in astronomy, optical astronomy, or otherwise, these things will be required. Okay. Basically, after you run, just copy paste from the notebook that we have provided you. Once you run this, you will have these uh, table with you. Although it prints only few of them, but total there are 11,820 rows. Now imagine you have to convert all of them from equatorial array depth to ecliptic latitude longitude. If you do it by hand by calculator, you will immediately resign from any astronomy dreams or whatever. But there are ways to for Excel sheet to Python to handle it. We will go through few of them, not Excel sheet of course. Right. So one is that you you have defined now. Okay, so one way is from the Astropy thing, but what we will do, we will use a for loop. So every time we check, uh, we iterate, take these two coordinates and then convert them, right? And we have defined an array. So this entire array of array J2000. What is J2000? It has to do with at what time of precision we have. Uh, it's a detailed thing. We will not worry about it. Yeah, so someone is anyways. So yeah, Gaurav, you can go ahead.
There's a question in chat which might be helpful to others as well.
Right.
What are we trying to do from Astropairing? If you can just tell that in one sentence and then
Sure.
the next cell.
So basically, don't worry about what is happening in this cell. What we are doing essentially, we are getting 11,000 uh, coordinates for stars that are near this region, near this array deck. So AstroQuery has a database of a lot of stars, their coordinates, and many other values, not just coordinates. But since we are interested in just coordinate conversion, we have tell AstroQuery, hey, give us array deck of all these sources that are near these this location, and in variable q, we have stored them. There are many. I mean, it's a long table, but we will take just a small one. So first index of q, which is the zeroth index in Python, is what we have printed, and we will work with that. In table, you can refer to different columns by giving the column name. This the table also tell you what units they are following. In this case, the table already knows everything here is in degree. So we will later see. We don't have to tell it much in detail. So you
So
can
some of the functionality that we are introducing you to here, we are not going to explain every single piece of it. We are doing that intentionally, okay? Because we wanted to stick to, for example, we could have also generated 10,000 random coordinates and asked you to convert those. But now that you have heard about AstroQuery, we hope that if you are interested in trying to download a list of sources like this, it will also have other properties which Akshat has not printed here. But if you are interested in things like those, then you will be able to actually look up more. So once you know the names of the tools that you can use, you will be able to go and use those tools yourself, find more information about them elsewhere, and so on.
right. So by this time, um, I'm assuming all these things have been done. You define your array tag as Q0. Then you want only the column which has the array. You find this in as a numpy array. You save it as a in variable array. So entire all these 11,800 numbers are stored over here. Similarly for deck, you can just copy paste this. And what we have done defined an empty list conversion, right? And what we will do every time we convert one pair to another pair in your different coordinate system, we will append that number in that list. So if every time you append, you insert one number your list to there. And what we are also doing here, we have defined a start time. So we are telling, hey, start your stopwatch from here, and by the time this code is executed, these two lines, uh, just end your stopwatch. So end time equal to time to time. That is what we are using our time library for, and we will then print. Uh, just a second, I haven't run myself a lot of these. So uh, so far, just copy paste stuff you have so far, and just run that and see what time it prints. All those who have finished running that code, just raise their hands. This is the last code we were at. A lot of your cells must be stuck at the last cell. Don't worry. That's the purpose of showing how things work. It will take you significant time for this cell to run, and that is because what it's doing, it's iteratively going one by one. So it goes over here, asks the table, hey, what all coordinates do you have? 56 point whatever, 1023 plus 0 and then it converts them into ecliptic. Then it goes to the next line, convert, extract these values, convert them, append, then goes to next iteration, and so on and so forth. And it goes to 11,820, all of them, and then finally it prints. So for me, it took 68 seconds or something. Okay.
Sir,
Yes.
sir, what does this percent capture does? This statement. So the first line of the 15th cell.
Uh-huh.
It suppresses unnecessary output. Like when we defined this function, we had added some print statements, right? So now that we are iterating over thousands of entries, it will go on printing all of those individually. So to suppress all of those outputs, we have added this command here.
Okay, thank you.
Note that this is a Jupyter command. It is not actually a default Python command.
There are other ways to suppress, but this will not help you in Python because we are printing a lot of stuff in the above things, all the ecliptic and all, so that we don't want. Otherwise, it will your Jupyter notebook will have a lot of print statements. Okay. That also consumes a little bit of memory. I learned this the hard way sometime earlier. All right, so it took us 68 seconds. I don't know how much time it took others, but roughly on the same order it will. Now let's do this separately. Now, what the Astropy module we have, where we have given, we have defined your variables, and then they go to a sky pod, right? This one will be more appropriate. Yeah, right. So we just say array equal to this variable times degree. So this variable can be one number, and this variable can also be an array of you know uh, thousands and thousand, 1 million numbers. Similarly, deck we have to make sure both the numbers here are same. Otherwise, it doesn't make sense. And then when you run this, yeah, when you run this command and your array and deck are defined a couple of cells above from the table, just when you run this, you get just in 0.02 seconds. So you just press enter and tada, you have the answer, right? Right. So it's like about 20 milliseconds, 24 milliseconds. That is huge difference. Something over a minute and something you don't even realize. Like it takes 200 milliseconds for you to blink. So it was faster than blink of an eye, literally. Right. So we have understood that just using correct library in a correct way can save you 3,000 times faster speed. It will save you significant time. Imagine if that was not 11,000, it was several million, and that's what you would expect if you are dealing with a lot of stars and you have to adjust it for different satellites, different cameras, different telescope. If you do this the hard way, just a for loop, uh, you will rarely finish your work on time, which there could be other reasons also. So yeah. So here we end first module of our discussion. These discussion were made by uh, Priti and Simran. So we thank them for this. All right. I believe all of you must have reached here by now. Now we will calculate other thing, angular separation. Before we start, is there anyone who has not understood or needs some help so far?
Can you all please lower your hands? And if you have any questions, just unmute and ask now.
Okay. Yeah. Is there something? Okay, so we will just move on. Angular separation. So if I give you two random coordinates on a Euclidean plane on a graph paper or on a sheet of paper, and I ask you to find the distance between them, it's easy. You can just do square root of x1 minus x2 whole square, whatever, you know the formula, right? If there are 2 points on a sphere and you want what angle they make with respect to the center, okay, uh, you don't have some similar formula, square root of 0.1 minus 0.2 whole square, whatever. Uh, so in this diagram, you can see there is point P, there is point Q. These are 2 points on sphere. They might not look easy, they're not easy to imagine, but consider them as on sphere. Uh, Both of them have certain latitude and certain longitude, represented by lambda and phi. You must be asking, why are you confusing with this notation every time? Well, that's how people work, because all these notations corresponds to some other part of the subject or topic, which conventionally or historically people have been using. So a lot of the formulas you will find still containing those convention. So it's also another lesson that yes, people use different variables for different uh, things, or for the same thing itself, or at some point you will realize you will run out of all the alphabets in Greek and English, and there will be more things to define. So you will mix and match a lot of things. Yeah. What we are interested in this angle, if you can put your attention to this delta sigma you have, this angle we want to calculate what these two suspend at the center, and we have lambda 1 and lambda phi 1 and lambda 2 and phi 2 defined for both. So we have these coordinates given to you, which are right ascension and declination, point 1 and 2, and these are their absolute difference. So lambda 1 minus lambda 2 uh, of absolute value of there is your these variables. Now we wish to calculate, in fact, delta sigma. So these are the formula. Doesn't look pretty nice and don't look like typical square root sine something, square something. And yes, there are sophisticated. This one looks terrible. I'm sure no one will be using this, but I assure you people are using this. So this is what we will be recreating. I will be using,
Akshat,
yes.
I think in the interest of time, let us go directly to the shortcut solution. So
Okay,
what I suggest is, so just as last time we started you with coordinate convergence being done manually, then we showed you better ways to do it. So there is also exercise 2. I strongly encourage that you try to do it yourself. But then we are going to go and show you directly how to do it with Astropy.
right. So yeah, thanks. That's a nice suggestion. So yeah, this will be a little bit tiresome. You will do something. I don't know if you had enough time to capture the solution. So we will do this exercise, and see
Don't
if you.
forget the cell above that.
Yeah, this is also important. Just run this, although you have, but in case you are running that in separate module. Uh, we are using two stars. These are well-known stars, Sirius and Betelgeuse. You can find them in northern sky very easily. So if you find online what are their coordinates, this is a kind of uh, representation you will find. We prefer in degrees. What is this? It doesn't look very nice. So this means if you divide your entire sky into 24 hours, or 360, instead of 360 degrees, you divide your phi angle into 24 hours, then every hour.
You are aware of these coordinate systems, right? Does everyone know right ascension declination in hours, minutes, seconds? Mahesh sir,
Hello.
do they know hours, minutes, seconds?
No,
Okay,
but
they know degrees,
Ye-
minutes, seconds though.
yes.
Yes, sir.
Okay,
yes,
so just as we use 360 degrees and then divide in degrees, minutes, seconds, astronomers kind of like to do weird things. We use magnitudes per square arc seconds as our units. We never use anything standard. We do everything in CGS and so on. So why leave angles in peace? So we use something called hour angle. which goes from 0 to 24. And just as you have degrees, minutes, seconds out of 360, we have the same thing in hour angle as well. Okay, but the job of a good library is to make sure that astronomers can annoy you only so much and not any more than that. So as you will see in the next line, you can directly enter these coordinates as hours, minutes, seconds, and degrees, minutes, seconds.
Okay. This is the exact syntax you have to use. If you write comma somewhere or write in a weird way, it will not work. Uh, Although you can define your own libraries in such a way. But right now, please follow this convention. There are no spaces. H for hour, M for minute, S for second, and D for degree. And just, although you already have access to, quickly copy paste. And this line will quickly calculate those gigantic formula we saw.
Is
They
it
will, yes.
4 decimal places only for seconds?
No, you can add as many.
Okay, I mean, just with 2 decimal places, you write as no problem, right?
Yeah. So if you even rounded it off as say 6 hours 45 minutes 08 seconds, that would also be okay. Or 8 seconds, that would also be okay. The important point is that there are no spaces in between.
Okay.
Yeah, so something like
So
this.
again, 08 is not required. 8 will do.
8 will do. Yes.
Yes. Okay. So I in fact forgot what was it's there, but whatever. You can play. You can add your own. Right? And you give it a frame. Um, it will not know what exactly these are. This is a sufficient pair to write. Uh, Same thing we have converted ourselves. There are again libraries that you can convert this notation to actual notation, which we have actually used to prepare them. And if you want, you can also do it with a numerical way. You can calculate them otherwise, and then just you say, hey, I want separation between C1 and C2, print them in degree, and there you have it. Right? As you can see, both have roughly, I think I have to rerun this again because I changed the numbers. Yeah, both are roughly the same because I have rounded off these decimals here. So after certain times, this will change, but that's significant digits problems anyway. So just because Python is giving you a long decimal thing, not necessarily that has physical relevance. So yeah, your boring
So
course
can
of.
you get output also in DMS?
Yes, in fact, if we don't do
In
this, if
does tabbing work in this, Akshat?
I no.
Okay, so later I will suggest that you all look at this as well. You can actually access them as sep.r there. So you can actually access them as separation.arcminute, separation.arcsecond. So if you want to access just the arcsecond of it or just the degrees of it, or you want to convert into weird units, deca arc minute or whatever, you see all of those options are available. Right. So in IPython in Jupyter notebooks, if you put dot and hit tab, then it will show you what are the different things that you can do. So you can get answers in giga arc seconds or whatever if you want. Why you would want to do that? Yeah, you might want to stick it back to the astronomers, but sure.
Yeah, so in Google Colab, I have just realized if you just type dot and you wait for some time, it will give you that list. Yeah, it will give you this list. But don't spend time reading all of them. When you are needed, just Google it. That will be helpful. So yes, you can also get this here. I think if you don't write print since only for Jupyter Notebook, it will work because uh, you don't print this in Python. Jupyter Notebook knows whatever is the last variable it has to print, and it can print you in these fancy terms. I like it sometimes, but I can't use it for several purposes. Right. So this way we can define a function. I will give array1 dec1, array2 dec2, array2, yeah, and I will define two sky coordinates. I will calculate the separation. Okay, and I will return them in degree. So we run, and there will be a function which we defined earlier, which we skipped for the interest of time, which we did manually and we calculated ourselves based on the formula. it gave us, oh, actually we didn't run it manually. This was the function, then you have some exercises to do. Right, so we calculate this based on manual calculation. Then this is for your exercise problem. You get something similar, and the Astropy ones again gives you similar values, and we have learned Astropy has many more advantages, mostly your coding writing things. So far, have all of you understood? Are there any problems? Raise hand if you have a problem, don't understand, or you're not here by now. There are no hand raised. Okay, so let's move on. So okay, so let's come here back. You remember Q0 was our table which has a lot of array and deck, and we will use to find the angular separation between one of the given coordinates. So I have used Betelgeuse, I guess. Yeah, I've used Betelgeuse coordinates. So I want angular separation from Betelgeuse for each one of them. So what is the angular separation from Betelgeuse for first pair, what is for second pair, and so on. And let's calculate. Just in case you don't know this feature, since every element in this table has uh, three inputs, three numbers or whatever, you can say, okay, for variable 1, variable 2, variable 3 in this table, let me assign them to these variable and then print them. Okay, there are other ways also. We have just for simplicity we have done this. So every time it iterates, it stores id into variable I, array into variable r, and definition into variable type. A reminder: this is just for simplicity, and it is not expected from you as a good programmer to use such a variable names I or t. That's very bad. That's very unintuitive and should not be used. This is just for quick understanding. And one more thing I want all of you to be on board. You can define your list in such a way. If you print your list, you will get what you have defined. But if you want to append, you can either use append function, which we have used earlier, or you can just write plus parenthesis, square parenthesis, and your new element. And when you print again, this will be added to your list, right? Something similar we'll be using. These are the coordinates, numerical in degree for R and deck for Betelgeuse. For all those 18,000, 11,000 numbers, we have calculated the angular separation. This function we have already made above, and whatever the value is, I store in variable x, and then I append in this fashion in variable SAP set, okay, which we have defined as empty initially. Let's run this and see what happens. Now there will be a question: what is this percentage time? It is Jupyter Notebook only nice decorator magic function commands, whatever you call them. It just tells how much time this cell took to run. So I was being lazy. Instead of writing start time equal to time dot time, end time equal to time dot time, I will just use this magic function. This is only for Jupyter Notebook and not to be used in generic Python commands. Okay, it took around 35 seconds, and it gave me an array of all the separations that I was needing. Somehow it printed them horizontally. 35 seconds is how much time it took, right? I hope everybody is here on board. If you're not, please unmute and say you have some problem, you are lagging behind, please talk for you, whatever. Now let's see how Astropy will do it. Although this was also using Astropy, but how clever use of Astropy will make it faster. What I have done, I have given the entire array in this variable array1 and deck1. And sky code, I have defined it in such a way that first variable is your array1, second variable is tag1. That is the entire array, not just one pair, all the 11,800 pair. So this C1 will have information of all the 11,800 coordinates. Second variable C2 is just one number, that is 88 point. You can also hover in Google Colab and it will give you the current value of those variable. So that over here is for the Betelgeuse, and I have not. It's another reminder. You have to give it the units, that is in degree. You can do u dot degree or u dot tag, both works. Since the table already knows that it is in degree, that will work. And I have just said calculate separation between C1 and C2. That means entire array of C1 and C2. So let's see what it does for us. I run it, and in 12 milliseconds, you get your entire separation saved in one variable. And see, it's like almost 2000 times faster, and it's easier to write as well, right? And you can convert them. Instead of degree, you can like save it some as a different quantity, arc second, whatever you need. And see, in fact, if you don't print this at all, I will comment it, the time taken will be slightly less. Oh, it's in fact more than the previous one. Right? Yeah. Sometimes on average it is slightly less. Order operations of milliseconds have some other errors within the other time consuming stuff within the computer. We will not discuss that, but on average it is faster. So if it's not required, it's recommended not to print, and that is why in one of the commands we cleverly used percentage capture to not print them and bother your graphics part of the computer to print them. And yeah, so if everybody is on board till here, if you understand what is happening, that's fine. If you don't, please raise your hand. So we are switching between two now. Once we say if you know everything, if you're done, raise your hand. If you don't know anything, raise your hand. So yeah, within the limits of resources we have. If you don't understand and if you're lagging far behind, you need some help, please raise your hand. Or in fact,
Sachin had raised his hand. Okay, if there are no questions, then we have one last module to go through. But here we are going to use a even faster trick, which is that we are only going to show you what is done there. And again, in the interest of time, we will let you explore it in detail. So what we now want to do is we want to calculate the position and rising and setting of the sun or some planets or something like that. Now remember that this becomes quite tricky because you first need to figure out what the coordinates of those objects are, then figure out when they are going to rise and set. Now those of you who have not had a direct exposure to astronomy and have not tried to do these kind of operations, congratulations. But when I teach a astronomy course here, for example, one of the problems that students dislike the most is a very innocuous sounding problem, something like what time is sunset today? Okay, and those calculations, if you want to do by yourself manually, are ultra time consuming. So Akshat is now going to walk you through some of them. We will hear, so we don't expect you to actually run these by yourself right now and follow along. So in 5 minutes, Akshat will just show you what is to be done, and we will close with that.
right. So uh, yeah, thanks. So for this, we will need one more library, astropy.time. Just run this, copy paste from our collab thing. And what we have also done is we have defined a date and we have assigned that date to a variable. Date we have chosen randomly, uh, 3rd of December 2018. Why is it not 12th of March? Well, that's the convention people use. And yeah, so if I just run this and print it, it will automatically assign midnight time to this date, because often date means you need both date and time. So that's a particular number or value in Python that we will require. For example, if you know, if you would like to see what's the time now, and if you just print uh, now in JD, in MJD, in decimal year, you will see 2021 dot, because we are roughly 40% of the year has passed. That is what it means. What is JD? What is MJD? Don't bother. Read sometime later. If you notice, it says like uh, fifth month, May 28th date, and the time is 10:15. That's weird. It's almost 3:45. So that is because it is using UTC time. In very layman common terms, it is using Greenwich or London time, which is slightly different from reality. But for simplicity, UTC is your prime meridian time, without the daylight saving and all those other things, weird things going on. So you have to remember that such thing exists, and if you want to add,
By the way, there is, yeah. Oh, you are showing that. Okay.
so if you want to add 5 hours 30 minutes to UTC time, because that's the time zone we are in, we will just say, okay, from now add 5 times unit dot h, that is r. You can also type r, h o u r, plus 30 dot thing, and it will automatically know. You don't have to multiply this into 60, divide everything, whatever. It's quickly done by Astropy. It automatically knows, and this is the place where it will be printed. Parenthesis 0. So whatever is the 0th element over here will be printed. So you can, so okay, in 5 hours 30 minutes from UTC, this will be the time. So now this is more closer, but this is the time added when I run this cell. So it is slightly few seconds behind what you would expect. So I think a couple of minutes behind. Anyways, some more important libraries. Please quickly run this cell, copy from our collab.
Right now they can just watch it, Akshat. You run it.
Okay. So yeah. So all right. These are again, we will require Earth location.
So you can guess what these are going to do. We are going to define a location on Earth. Then we are going to get ephemeris, that is how an object moves with time. We are going to get the sun. We are going to get the moon. So if someone tells you to go get the sun or aim for the moon, then remember Python can do that for you as well. Um, okay, so
virtually.
let's define Mumbai here and proceed.
Right. So what we have done, we have given latitude and longitude of Mumbai. That's fairly round off. Mumbai is not exactly 19.000 degree. That was just for simplicity. This is, I guess, height in meter, how much above sea level we are. We have also told it at what time we need these ephemeris, what time we need these coordinates and position, and from what location. So that body, which we have already imported, we just tell the Python to just run, and when we print it, this is what we get: some sky pod with a lot of information and location. These three numbers are actually what tells where the Venus is exactly. We will worry about all these things later. Anyways, this doesn't look very nice, so let's convert them into alt as. Alt as are just fancy coordinate names that tells exactly how, with respect to as an observer, if you are standing in Mumbai exactly at 19 degree and exactly at 72 longitude and exactly at 14 meters, at what angle with respect to horizontal you will see Venus in sky, and what angle with respect to your reference will you see your Venus. So that is a much more interesting and useful angles. So if you just run them and print them, you will see that at 61 degree 4 minute 45 second is your altitude. So 61, so slightly above halfway is where you will see Venus right now. In fact, you can't see because sun is too bright, and 285 azimuth is what you will observe.
So
Okay,
this is something which you can actually try again tonight. So if anyone remembers the time for sunset, then you can create that date, that time variable. Instead of time dot now, you can say time off and give the sunset time in UTC. It will tell you the altitude of Venus at sunset and the azimuth. Now 270 is due west, 360 is north again. So you are, what this is telling you is that this is slightly to the north of west. And if you solve it for the evening time, then you'll find out that Venus is going to be something like 20 degrees above the horizon when the sun sets. And you can actually look in the west. Mumbai happens to be cloudless today, so you could actually see where it is.
Yeah. Just make sure you are in a less polluted city and no high-rise building. Go to your roof. You're in a suburban or rural setting. That will be nice. So you can actually spot Venus and at some time Mercury. You have to have probably binoculars for that. So this can actually be done.
One question.
Yes, please.
See, we are writing in with hands the right ascension. No, not the latitude longitude of the place.
Mhm.
So, does any library uses GPS and gives
There
you
are no, there is no GPS library because that would require your computer's location and so on. However, the standard observatories
okay?
can be
Those
loaded
will
by
be there.
name. So we can load, for example, Growth India Telescope or Himalayan Chandra Telescope, Keck, Palomar, whatever. Those can all be loaded by name.
Okay.
Okay. Yeah, but if you, let's say, you want to store somewhere all the latitude, longitude of important places, sites, you can be very precise, like exactly Jantar Mantar you want, so you can provide that and it will give you reasonable answers. Several astronomers, amateur astronomers I know use this for their sighting. So what we have done over here, we have defined a time which is roughly evening time, 6 p.m. This is the, you have to remember, this is the UTC time. So, but what we have done, we have uh, done, we have also added a lot of numbers to it. So if I just add 1 to this evening date, if I should also print evening. So this will give you I think anyway, so you can store this. This is also a number which you can use it. We will see it later. So this is essentially a number. Here it is printing as that thing what we have defined, but you can if you add 1 to it, that will add 1 day. So or not, Gaurav, it will adding 1 will add 1 hour or 1
No,
day.
no, no. You'll need to give a quantity. It will give you an
uh,
error.
right.
So right now we are adding in 30 hours we have done 300 divisions. So
Right,
that's
right.
it's going
Okay.
to
Yeah, yeah. So
add.
you define R to it. Correct, correct. So since we have multiplied this to R, so when I add uh, gap to evening, it will give me 300 such numbers, range from adding up to 30 hours, from 0 to 30 hours every 3 for 1 by 300th of a 1 by 10th of a hour. Right. So this is the array we will get, and so we can then get, instead of getting iteratively your position at every instant, we can get coordinates of Venus at every this instant for entire array. This is what we are trying to do. So what we want is altitude and azimuth for observation time for this entire array that we want, and for this location we want. Right. So we have defined some local variable, and in this local uh, structure, what do we want? We want the coordinates for Venus, again for evening.
So note that Venus and all of these other objects are actually moving as opposed to stars. So their sky position is not changing only because the Earth is rotating. They are actually moving with respect to background stars, which is why this get body actually has to be run to get the exact positions throughout the night. But as we calculated for Mars, Mars moves barely half a degree at night if it is at opposition. So what you can do is, if those approximations are okay, you can skip that line in between.
Right.
Just
So
run it,
yeah.
Akshat.
So get body will get you that weird stuff which we saw earlier, a lot of numbers. We have asked it to, hey, transform this to local, which is where we like to have altas, and we have defined what our location and time are. And if you print uh, we'll add, for example, we will get the altitude of Venus at all distance. There will be 300 such numbers. You don't have to worry about ranging from entire 30-hour cycle, but we will, for now, not worry. We will assume Python is doing a good job and it stores all of these. And yeah, similarly, we have also dedicated function just to get sun. So instead of writing get body and sun over here, we have a special function just to get sun. Also, this has to be imported. And similar thing for moon. So now we have basically done. We have stored altitude azimuth for Venus, Sun, and Moon. And your next exercise would have been, if time would have allowed, to plot these as a function of time. So here you can see Sun and Venus are fairly close to each other. That is why once the sun sets, like if it is around 0, that is exactly at horizon, you see at that time you still have Venus above horizon. So you will still see it, and probably from naked eye, if there is no much haze in the background. Similarly, moon or something. And the other part you will notice that at least for moon, it's easy to see things are periodic. So roughly 24 cycle. It should not be 24-hour cycle for moon. It's moon also moon. But roughly 24-hour cycle, you see things repeating, right? And that's confirms that okay, all of your code and everything is running correctly. We have extracted this value nice and fine. And from this, you can do your calculation. Take out for observation, since moon doesn't go very high in the sky. You know, if you are in a place where there are a lot of high-rise buildings, so you know accordingly how to set up your telescopes or binoculars or nighttime stargazing or whatever. So yeah, this was a quick stuff. Quickly understand how things work. A quick refresher to Python libraries, what astronomers do for living. Uh, we would I'd love to give you another exercise to see how these things change over a year. You can do at luxury of your own time. That's all from all of us. I hand it over to Professor Varun. Unless you have any questions, any doubts, anything to ask, comment.
Thank you, Akshat.
Yeah.
Can I share my screen now?
Yes, please.
Okay, so I'm back. We have the last few minutes left, so I'm just listing a bunch of links here that we talked about. Google Colab notebook that we used. We will also put solutions to your tutorials here, but not today. We will put them after 2 or 3 days because we have left 2 of the exercises as homework. So hopefully you will work through that. This is the link again to the Google Collaboratory that we used in case you don't want to install all the libraries offline and you just want to do these things directly. We talked about Python formatting. Later, Akshat mentioned this thing in brackets, in curly brackets, he had written 0. So I just realized my video is off. Okay, there I am. And yeah, so those formatting details can be found here. Astropy coordinates, this is the link where we'll share these slides so you don't have to worry about taking screenshots or writing down all of this. This is everything you can do with coordinates. Even if you're not an astronomer, this is cool enough simply for converting degrees, minutes, seconds into decimals, okay, in any part of physics where you're using those. Few tips about programming, okay. It's programming is something that we often learn on the job, but it is worth taking the time to learn good coding philosophy. What are good coding practices? What is object oriented programming? Why write code in a certain way? In the functions over here, you'll find that there are things written which appear red in your Jupyter notebooks, which are written with triple quotes. Those are called doc strings. What's the importance of writing them? How do you write code that you will be able to understand yourself 2 years down the line? Okay. Then another thing which I learned when I took for the first time I took a formal Python class, this is what the instructor told me. Okay, good programmers write good code, great programmers write no code. What does it mean? If you can help it, don't write code. Okay, use libraries that someone has written, other packages that have been written, and so on. Only if it doesn't already exist, then do it yourself. We have seen very nice examples of this today, where using a library you can make things 100 times, 1000 times faster as compared to writing your own code. So remember, even if it, so often when you are starting a project, okay, especially as a student, something you want to do in a quick and dirty way, is very, very tempting to first just try and do those calculations yourself. But remember that if it is any good, then you will build upon it. You'll go forward and do more and more stuff, and that is when it starts becoming extremely unwieldy. So you really don't want to do that. Okay, so use libraries everywhere you can. Astropy, Matplotlib, NumPy, all of these are libraries. And then finally, practice, practice, practice. Okay, play around with code. Don't wait until the last moment when you actually need your code to do something, and at that point suddenly programming shuru karoge, so that's not going to turn up very well for you. So find fun challenges to work on, do random programming just because you can, so that when it is time when you need that programming skill, you already have it. Okay. If you want to learn more, starting with Python itself, go to the official Python website. They have a whole lot of tutorials and links and material there. There are a lot of other free resources as well. For example, Code Academy is a website where they have free and paid things. This is not an affiliate advertisement. What I liked about Code Academy though is it gives you a terminal within the browser where you can try things if you want. I think all of you are probably beyond this stage. Resources here will still be useful. Books, computational physics, how do you do this, is a very nice book, very popular. You may have heard about books like numerical recipes in C and Fortran and so on. A lot of those things are not very good for beginners. And the way most of us will use codes these days, you don't need to know those things right at the start. You do need to know them later, because otherwise you'll fall for different pitfalls in programming. There are other books, best practices for Python development, Hitchhiker's Guide to Python, Effective Computation in Physics. So these are general Python for physicists or computation for physicists kind of books. Nothing astro specific here. Um, One of my colleagues, Professor Robert Quimby at San Diego State University, has put together these nice resources, very good tutorials for everyone. For okay, okay, so it is called Astronomical Techniques, but he starts with Jupyter notebooks and videos about everything. Okay, so how do you use debugging? What is FITS format? How do you use Jupyter notebooks? Goes into statistical analysis, least square fitting, more details of statistical analysis. So a very good set of tutorials. And then he has a bunch of bonus tutorials here as well. So this is the link for that. If you are an astronomer wanting to do Python, then this is a fantastic resource. Another of my colleagues, Professor Tara Murphy in Australia, has given this excellent course called Data Driven Astronomy. You can go and take that course, it's free. Astropy itself has set up a lot of nice tutorials. Go to learn.astropy.org. And then our research collaboration, Growth, which is what Tara Murphy and Robert Quimby are both part of. This stands for Global Relay of Observatories Watching Transients Happen. In 2018, we held the first ever Growth Astronomy School at IIT Bombay right here. Since then, for the last 2 years, we have held these schools at various places around the world. And here is the website. So if you go here, then you will find all of these materials. So for example, here are let's go to the latest ones. So if we go to the resources from the 2020 school, again, you will find lecture videos. These are now heavily astronomy centric. Okay, so you will find that we start with Python basics, but image processing, photometry, how do you prepare for observing runs, image subtraction, spectroscopy. There are notebooks on X-ray astronomy, analysis of variable stars. And with all of that, you have YouTube videos and you have the Jupyter notebooks themselves, which you can download, and you can do all of that by yourself as well. And then the last thing that I want to point out is that IIT Bombay, the astronomy club here is called Kritika, and they host this thing called Kritika Summer Projects. So if you go to their Facebook page, then last year's projects, and you'll find some useful videos and so on there. So here's the announcement from last year that they had, Kritika Summer Projects. And so they had their schedule and all of their tutorials and so on. So they taught a lot of things as well, starting from basics of Python, but then switching into astrophysics. So if that is something that is of interest to you, then you can look up those resources here as well. So that actually takes us 5 minutes past the hour. So we will stop now, and we can take any questions that you have.
Before I forget, I would like to thank Gaurav for the last module you saw. So Gaurav, Kriti and Simran, thank you for preparing all these modules. Yeah, we can take all the questions. Ask anything. You can. There is no stupid question. You can ask. Is Python so boring every time? We have to do this. Anything. It's okay. We understand.
Sir, can you please quickly highlight the recent research is going on in astronomy and astrophysics?
Oh, okay. No, because sorry, that's not the answer that you expected. But there is a lot going on, and trying to highlight that in 2 minutes would just be a disaster. What I can do instead is I can point you to two resources where you will get a much better answer than this. Okay, the first is a blog called Astrobytes, and you will find out details there. Astrobytes.org. This is a resource this is a blog that is maintained by PhD students for undergraduate students. Okay, so it is meant to be read by BSc MSc students. And what these people do is that when anything cool new happens in astronomy, when there's a new research paper published that is particularly interesting and so on, they will actually summarize it as a blog post. And that is an excellent way to get a flavor of what is going on. Um, it's very difficult for say a BSc student to actually directly start reading papers in astronomy. We publish about 60 or 70 new research publications every single day, so it's impossible to be on top of that. Astrobytes is the place where you can go. There is another thing called AAS Nova, which is a similar thing. It is essentially a press release channel by the American Astronomical Society. And then, of course, NASA and ESO News and so on. We'll talk about more on the outreach side of things. But there is so much happening in astronomy across fields, in exoplanets, in X-ray astronomy, in optical, in high redshift universe, Milky Way structure. Our understanding has changed drastically thanks to the Gaia mission. There's gravitational wave astrophysics. We are getting new insights into laboratory astrophysics, better understanding of plasma. There's just way too much happening to try to summarize.
Okay, sir. It answers. Thank you.
Welcome. Jigar, you can unmute and ask it yourself.
Hello.
Yes, go ahead.
Yes. Yeah. So my question was: Is machine learning useful in astronomical data, and if so, what are the uses?
Yes, machine learning is being used in various aspects of astronomy now. One place where we are using it, for instance, I showed you some of those images where we had gone through data and looked for new sources, new explosions, so new source pops up in the sky. When we run our basic programs to find such sources, okay, in that data that I showed you, 10 nights of observation, we found about 2 million candidates. Okay, and going from that, finally we found 5 genuine good cases. So we did all of that with old-fashioned algorithms and so on, but right now we have a student who's working on applying machine learning algorithms to that, and various other groups have done it. So we'll be adapting those into our use. So there is machine learning being used there. In LIGO, we have something called glitches, and there are machine learning codes that are used to identify glitches. These are two of the examples. People are trying to see if gravitational wave data analysis itself can be done with artificial intelligence. So there are some applications. But this is one I'm so that is the answer to your question. Now going beyond that, we will also I want to point out something which I have to tell young students every time. Machine learning is not a magic wand, okay, and it is not a hammer that you should use for hammering everything. For example, if you want to convert equatorial coordinates to ecliptic coordinates, I can get 10,000 equatorial and ecliptic coordinates list. I can unleash a machine learning algorithm on that, and it will figure out how to go from A to B. It will not tell you what was happening, okay. And that means that you have no guarantee that it's always going to work. In particular, if I give you coordinates that are always say between minus 30 to plus 30 degrees, so that you don't have to worry about the singularities near the pole, I can guarantee that how much ever training you do, when you get that outlier case because it was outside your training parameter range, that is not going to give you the correct answer for that. Okay, so just because machine learning is fancy, just because artificial intelligence is fancy, does not mean that it is the right tool for everything. There are certain classes of problems, face recognition, for example, where machine learning is really good. There are other classes like coordinate conversion, where machine learning is a really bad idea. So you have to make sure that you understand. So this is not in response to Jiga's question. This is a general word of advice or caution, that you have to make sure that the problem that you are addressing actually needs machine learning before you try to apply machine learning to it. Okay, Nishta has a question. Nishta?
Yes, sir. Can you guide us on how to pursue astronomy after BSc?
Okay, again, not relevant to the current session. So maybe we'll take a few more questions, and if there's time, we can come back to it.
Yes, sir.
Varun? Varun Sohanda?
Yes, I was asking like you mentioned about the things which are done using Python, like some of the projects you have done. Does all the projects done in Python use some or the other library?
Okay, so this goes to the definition of what a library is, right? Anytime you make any useful program, you'll package it off as a library so that others can use it as well. For example, if you have programmed in C or something, then without a library, you can do pretty much nothing, right? You'll at least import stdio, you'll import math or whatever. Okay, so libraries are used because it's a good thing. We have done parts of today's tutorial without libraries. We did for loops where we still, and for example, without numpy you will not be able to do pretty much any serious astronomy calculation. So numpy is a bare basic library that you must use. We use lists. Lists are a native Python object. So uh, must we use a library for everything? By itself, Python useless hai, is not the right way of looking at it. That's like saying, must I use a computer for everything? Without it, Python is useless. Yeah, of course, you need something to run Python on. Libraries are nothing but codes that have already been written, tested extensively, made optimized, made very efficient. So you can do all of this from scratch. Okay, you can, in fact, you can decide to do all of this in vanilla Python. It will be ultra slow. So people who care about this have put in all the effort to really write good level code. So why not use it? Does that answer your question, Varun?
Yes, I got it.
Sir? Hello, sir.
Yes, Bidi.
I have a doubt. Like, if we have a set of problem and
Mhm.
we can code it, but if we want to use the library, then how will we realize what is the exact match of that library which we want to use for our problem? Like, which
Uh,
library is more accurate to our problem? How do
calculus
we
किया
know
है?
this?
Have you done
Yeah.
calculus?
Yes, sir.
Okay. So I want you to integrate 1 upon 1 plus x square. What will you do?
1 upon.
1 plus x square dx.
Okay. So I'll try substituting
Correct. How do you know what to substitute?
by learning
So there
various
are
types.
two ways.
Yeah.
There are two ways in which you know how to substitute. Way one is trial and error. Way two is that you just know. right? You ask around and by now everyone is like, हाँ 1 plus x square है तो ये वाला substitution करो तभी होता है वो integral, right? So same kind of ideas apply here as well. If you are looking to do something in astronomy, very likely the place to start is AstroPy. If you are trying to do something numerical, the place to start is NumPy. Plotting, Matplotlib. There are libraries built on top of libraries, by the way. There are things like views and so on, or pandas, which are built on top of existing libraries to make calculations even faster or make things even easier. Okay. The answer to your question so is that there's a basic framework that tells you where to look. You can go and look at AstroPy documentation. That is why this learn.astropy.org site that I told you, it tells you what the broad scope is. To know exactly what to use within the library, of course, you have to use the manuals, right? There's not going to be a random Akashwani which tells you, okay, to do coordinate convergence, you have to use astropy.coordinates.skycoord.transform underscore 2 dot geocentric to true ecliptic. How do I know that? How does Akshat know that? We read the manual. Okay, so that is where you'll have to look. Of course, these days you will do what everyone does. You go online and you search first, saying I want to do this. There are also very good active forums, by the way. So, for example, AstroPy has a very active mailing list where people actually help each other quite a bit. We have had cases where we needed a certain functionality in a library called HTM, hierarchical triangular mesh. That functionality did not exist. We posted on AstroPy. The library developer reached out to us saying, hey, this is currently not supported. Why do you want it? What do you want? And he actually updated the library to do this. Right. So this goes back to Varun's question as well. That is what a library is. We could have written that code by ourselves, but that guy knew better how to do it. And he thought, oh, this might be useful for others too. So he just added it into the library. Similarly, on Facebook, there are groups called Python users in astronomy and so on. So you can look at those options as well. Does that answer your question?
Yes, sir. Thank you so much.
I think Anant or someone had a question as well.
Yes, sir. So
Yeah.
what I wanted to ask was, are there problems in astronomy or astrophysics which are computationally very resourceful, like which cannot be done just because there's too much data or the complexity
Oh,
is too
there are
much?
a lot of them.
So
For example, if you want to simulate what happened after the Big Bang and how did galaxies form, right? Structure formation, computationally extremely intensive. LIGO data search, computationally extremely intensive. There's a new radio astronomy project coming out called the Square Kilometer Array, and there's a predecessor for it called LOFAR, Low Frequency Astronomy Array. The amount of data that they gather and the amount of computations that can be done with that data are so intense. The volumes of data are so large that radio astronomy data is not even often stored in the raw format, because you are talking of terabytes per day kind of data usage. So there are a lot of problems that are just waiting for efficient algorithms and so on to solve.
yes,
Many things.
so where I was coming from was, is there a way, or is there any scope of applying quantum computers or
Uh,
using them
Quantum
to?
computing, same thing. It's not a magic wand that will solve all of your problems. Quantum computing is
Yes,
good for a certain set of problems, not for everything. And the second part, it doesn't currently exist.
yeah.
Okay, so yeah.
Sir,
Yes.
sir, I have a question.
Yes, go ahead. Sachit, yeah.
Sir, we have seen this kind of various type of software we use we use obviously programming language like Python and more software packages. Sir, these are so software uses. Are there any hardware limitations? Obviously, our PC cannot handle all big data that we require to store.
Correct. Correct.
So, what are those modern hardware that we use most of time in
We
astronomy to?
use something called computing clusters. So these are supercomputers essentially. So lots and lots of machines added together. Ayuka cluster we were just talking about the other day. So my laptop, which I'm speaking from, has a 500 GB hard disk. Okay, and it has some 16 GB RAM or something like that. The computing cluster that we use at Ayuka for astrosat related analysis and other things, that has 384 GB RAM. Okay, so its RAM is almost as large as my hard disk. So there are high-end computing clusters that are used. We are also exploring using things like Amazon Cloud Services and Google Cloud Services and so on. So cloud computing is also coming in. For certain radio astronomy applications where processing is ultra intense, we use thing called Roach boards, which are highly customized FPGA based applications. I'm working on an X-ray satellite right now called Daksha, where onboard computing will be done using FPGA arrays. Um, Graphics processing units, GPUs, are used for a lot of astro calculations, for specialized astro calculations and so on. Okay, maybe I have time to come back to Nishta's question, astronomy career and how do you get into ISRO without a BTech? ISRO is very broad. Okay, for example, if you say how do I get into IIT, the question is okay, JEE de do. There you are implicitly assuming you are coming to IIT for learning, right? So to get into IIT means, do you want to come as a faculty? Do you want to come as someone who works in the lab? We have people across everything, right? We have people doing security, we have people driving cars around. So similarly in ISRO, you have the full spectrum. There are people who are from engineering side, there are people who are on science side. ISRO has some astronomers, it has atmospheric physicists, it has geophysicists, it has geologists also, I think. Then there are engineers from different areas, materials, propulsion, electronics, mechanical engineering. So ISRO has a careers section on their site, and there's a large range of job options listed there, and ISRO gives out its ads annually. So you look at something and you find what profile will match you, and you can apply from there. Pursuing astronomy as a career, again, detailed answer would be too long. You can actually look me up on YouTube, and you'll find my lectures where I talk about astronomy careers as well. So you could just see the full details there, where I've pointed to various astronomy institutes in the country, what are the career options that are available, and so on. Meanwhile, another place where you could look at for some more astronomy, Gaurav just pointed out that there's Ayuka Astronomy School going on right now, and a lot of these lectures are, some of them are done, some are still going to happen, and all of this is happening live online, so you can go and join that as well.
Thank you, sir.
Sir, sorry, I lost my connection. That's why I think
Yeah.
I may have missed your answer.
There is a recording you will give you, but Varun, you
Yes,
can.
sir, I know. I just
So sorry, what was your
conveying this.
question again, Sachin? Okay, okay,
I was just conveying this message. Thank
okay,
you.
okay. Welcome. So we have gone well over time. Probably we can wrap up now.
Yeah, thank you, Varun. Thank you, Varun and company, for having this wonderful session about how astronomy can be done and lot of astronomical calculations. You have shown an incentive for people to learn Python. Okay, that you want to make a career in astronomy. These are all different things that you can do. And when you were answering that particular question about how do we learn new things, okay, so Python is a language, and every language, when we learn, it is the same thing. Most of the words, the present generation and even my generation who are learning from Urban Dictionary never learned in school. Okay, so we learn it by usage, we learn it by talking to each other, we learn it over the referring to
That's a
net.
great point. Yes.
That's, yeah. So that is what how we learn in the modern system. So thank you for exploring and exposing our students, the participants, to this interesting field. Thank you very much.
And also thanks to Akshat, Gaurav, Kriti, and
Akshat,
Simran.
Gaurav,
They've
Kriti,
put in
and
a lot
Simran.
of effort to make
I
these
said that,
tutorials and
I
stress
said
test
that
the
with Varun and
tutorials
team.
to.
So when it,
Sorry?
I said Varun and team. So yes, these
No,
people.
that was thank you from my side. Sorry.
Okay, okay, okay.
Additional thank you.
Okay. So thank you.
Thank you. Bye all.
Bye.
Thank you, sir.